So I'm going to tell you about extended weak order. This is a story about Coxeter groups, and it's an especially interesting story for infinite Coxeter groups. So the first part of the talk will be kind of telling about the more classical story of infinite Coxeter groups and root systems. And then I'll tell you why we should care about this extended weak order and what it is. But you can think, if you're already familiar with Coxeter groups, this is going to be a way of like completing the elements of the Coxeter group with some new elements that are very geometrically natural. So that's going to be where we are headed. So, oh no. All right, perfect. So yeah, to begin with, let me tell you about root systems. Root systems and Coxeter groups go hand in hand. And the way that we'll build root systems is using reflection operators. So if I'm imagining a reflection operator, then I'm imagining I have some like plane or hyperplane in, say, Euclidean space, and I want to do an orthogonal reflection over that. But I'm actually going to want more general reflections. So instead of thinking about orthogonal reflections in Euclidean space, I'm going to allow myself to just have some symmetric bilinear form. It doesn't need to be positive definite. And I'm just going to use the exact same formula that I would do for orthogonal reflection in Euclidean space. I'm just going to use this bilinear form instead of dot product. Okay, so if I do that, and I start out with this blue vector alpha, then I'll say that reflection over alpha is reflecting over the hyperplane orthogonal alpha. And the formula for that is just this guy, but we don't need that. Okay, so what is a root system? So it's going to be a collection of vectors called roots, such that if I reflect any root over any other root, then I get another root. And I'm also going to ask that any line contains at most two roots. So we end up with these highly symmetric arrangements of vectors. And so the blue arrows are the roots here, and I've also drawn the like hyperplanes orthogonal to the roots separately in black. Here's just another example. This one has 8 roots and also 8 reflecting hyperplanes. And you'll notice that, of course, these planes are planes of reflective symmetry for the root system. And I'm going to call that arrangement of planes that's orthogonal to the roots the Coxeter arrangement for the root system. So we'll see that come up again. Okay, so that's a definition for finite root systems. It's a little bit technical to properly define infinite root systems, but the most important point is that it still has this property that if you take a root alpha and a root beta and you reflect beta over alpha, then you get a third root. So they're still preserved by reflections over the individual roots. Okay, so I'll define the vowel group of the root system to just be the group you get by taking these reflection operators and just taking the group generated by all those reflection operators. So this is just some subgroup of GLN. And there's a regularity condition that we don't really need to be concerned about, and we'll still ask that in every line there's at most 2 roots. So here's an example of an infinite root system. This is called the affine A1 root system. So to denote an affine root system, there's a tilde over the letter. So whenever I say affine letter, I just mean put a tilde over the letter. And I'll define this for you later. But this is what it looks like. And again, the blue arrows are the roots, and the lines are the Coxeter arrangements. Okay, so this while group is very interesting. So this group of that's generated by the reflections over the roots. It actually turns out that while groups are certain special groups called Coxeter groups. So by definition, these are groups that come with a set of generators and have a very special presentation where we're just asking for products of generators to have some order. Okay, there's a nice classification of finite Coxeter groups which people are probably familiar with, the A, B, C, D, E, F, G, H, I. And you can do some nice things with these. So type A is the symmetric group, which I'm sure everybody's familiar with. Okay, so what are these affine Coxeter groups? So if I start out with a finite root system that satisfies a certain condition, being crystallographic, so all that means is that there's some basis for the roots, so that the entire root system is contained in the integer span of those roots. Okay, so if I have one of these finite crystallographic root systems, then there's a way of turning it into an infinite root system. So I'm turning a finite root system into an infinite root system in a procedural way. So it's the procedural way is I put a tilde over it, right? Yeah, okay, so how do I actually do this? Well, what I'm going to do is I'm just going to add translates of the original roots by some new vector delta. So if this is my starting root system, I have two roots, the two blue arrows. I'm going to put them in a vector space that's one dimension higher, so I can go in like a different direction, and I call that new direction delta. And then I'm just going to translate my original root system by copies of delta, and I'll end up with this picture. Okay, so just to do an example, the symmetric group is a Coxeter group. It comes from a root system. The root system is this set of vectors right here. So EI minus EJ for our standard coordinate basis. And it's crystallographic, so we can do this procedure. We can turn it into an affine root system. We get the affine type A root system. The Weil group for that affine type A root system is the affine symmetric group. And as you can see, the pattern continues. We just put tildes over everything. So if I do it for this is the Coxeter arrangement for S3. Then I get a very nice picture over here. This is the Coxeter arrangement for affine S3. So you can see you get some nice geometry from this, and we'll see more about that in a minute. So questions about root systems before I move on to week one? Okay. So the first thing we're going to want to do with our root system is split it in half. So we're just going to pick out half of the roots that we'll call the positive roots. And you need to do this in a certain way when you're in an infinite type, but it doesn't particularly matter for us. Okay, and the roots that are not positive are called the negative roots. So we have positive roots, negative roots. All right, now I'm going to care about certain special subsets of the positive roots. The special subsets that I'll care about first are called separable sets. So a set of positive roots is separable if there's a hyperplane which separates it from its complement in the positive roots. We'll see an example in a second. Another way of saying this is that there's some linear map from the vector space the roots live in for the real numbers, which sends the roots in my separable set to a negative number and sends all the other roots to a positive number. And there's a geometric interpretation for these guys. These are going to correspond to regions of that Coxeter hyperplane arrangement that we were looking at. Okay, so let's see this. Over here on the left, I have the A2 root system, the one for S3, and its Coxeter arrangement. And I'm just going to write down the separable sets. So how am I going to do this? Well, I'm going to start out imagining this. I have this little green man right here, and the little green man currently can see all three of the roots. And as he moves through the Coxeter arrangement, his view of some of the positive roots will get obscured by some of the planes. So as he moves around, the separable set that he sees will change. Okay, so he's moved to every region and he ends up back at the top. And these are all the separable sets he's found. So these are the separable sets for the A2 roots. So they correspond to the regions over here.
What defines what the green man can see?
Yeah, I wasn't really going to say that. Yeah, so when does his view actually get obscured by something? It's when he crosses the plane that's orthogonal to the root. Yeah. So yeah, each plane only obscures one root. Even though it looks like, okay, yeah, I was being a little bit ambiguous. Sorry about that. Yeah, each plane only obscures the root that are orthogonal to it. Okay, so now I'm going to define a partial order on a Coxeter group by relating the elements of the group to some geometry. So how am I going to do this? What I'm going to do is I'm going to write down a separable set associated to each element of my Weil group. All right, how do I do this? Well, there's a definition. So what it says is that I want to take the positive roots so that if I hit them with W inverse, then I end up with a negative root. So there's this action of the Weil group on the roots coming from writing W as a product of reflections, and we know how reflections act. And I want the positive roots that are sent to negative roots. Okay, so now I can turn my elements of my Weil group, say my permutations, so I'm thinking about the symmetric group, I can turn those into sets of roots. And that's called the inversion set. Okay, and then the weak order is just putting W1 less than or equal to W2 if the inversions of W1 are contained in the inversions of W2. Okay, so what is this ordering? It's basically the containment order on these inversion sets. So over here, if I turn, say, my permutation 213 into an inversion set, turns into that guy. And so I can see that it's less than 2, 3, 1 because this inversion is one of the two up here. Right, and over here I've listed the braid arrangement. There's like a way to biject the permutations with the regions of the braid arrangement that is very big. Okay. And I just want to mention the roots for affine A1. Also, we split them into positive roots in a similar way, so we're going to split them in half. In this case, I'm taking the top half. And again, by definition, these are starting out with the original root system, which was just plus or minus alpha 1. And then we're taking translates by delta. And it turns out that when you split them in half, you get the positive roots, you end up with negative alpha 1 plus delta as one of the roots. Okay, so that was the root system for the affine S2 Coxeter group. And so we can talk about the inversion sets of elements of the affine S2 Coxeter group. So these are what elements of affine S2 look like, and these are their inversion sets. And so you can write down the weak order by just looking at the containment order. Okay, so we get this sort of U shape, two chains going off to infinity. And I put the Coxeter arrangement on here for comparison purposes. So there's a way to line up the elements over here with the regions over here. So I mentioned that regions give us separable sets. I also mentioned like group elements give us separable sets. But not every separable set coming from a group element is coming from a region. So you can see up here, the regions shaded blue are the ones that actually correspond to elements of the group. There are more regions that do not have a corresponding element of the group. Okay, so I'm going to make it up. Oh.
That's different than the finite case.
That's different than the finite case. Yeah, so I'll say that formally later, but yeah, in the finite case, every region corresponds to an element of the group.
Yeah,
exactly.
And sorry, the separable sets do correspond to regions?
Separable sets do correspond to regions.
Okay.
Okay. So just sort of a reminder. We probably all know what a lattice is, but maybe we don't know what a complete lattice is. So I'll say that a partial order is a complete lattice if I have a least upper bound for any subset of any size. It can be infinite, and the greatest lower bound also for any subset of any size. So just an example, this guy is finite, so complete lattice means the same thing as lattice. And this is the diagram for weak order on S3, and you can see that it is a lattice. There's least upper bounds and greatest lower bounds for any elements, any sets of elements. Okay, so it turns out that for finite Coxeter groups, the weak ordering on the elements of the group is always a complete lattice. But as we can see from this affine S2 example, that fails when we have infinite Coxeter groups. So this guy and this guy do not have a common upper bound, much less a least upper bound. Okay, so we're going to make this, we're going to interpret this statement of the failure of the lattice property as saying that the weak order on an infinite Coxeter group is actually missing some elements that we should have included. So we're going to try to figure out what these missing elements are. Okay, so the first thing I want to do is kind of show analogs of these pictures in higher dimensions. Let's see if I can do this. All right. So here is the affine S3 Coxeter arrangement. So the elements of the group are in bijection with the triangles in this picture. This picture should extend off to infinity in all directions. And there's a way to biject the elements of affine S3 with the triangles in this picture. Okay. So yeah, what's going on? How does this relate to the pictures we were looking at earlier? Well, the first thing we need to realize is that when we look at these two-dimensional pictures for a rank 3 Coxeter group, we're actually looking at a two-dimensional slice through a three-dimensional hyperplane arrangement. So the first thing we want to do is think about this picture in 3D. Okay, so this is now a 3D hyperplane arrangement. And when we're thinking about it in 3D, we can talk about all these triangles that go off to infinity, but we're actually missing some of the regions in this picture. So there's actually regions on the back. So not only do we have these regions that correspond to elements of the group, but there's also regions on the back. And also in the middle, between kind of like all the hyperplanes, there's this plane that lies at the boundary between like this half and this half. And there are in fact 6 more regions in that plane. So we're going to want to include all of these guys as elements of our what will end up being the extended weak order. And the goal will be to add elements that come from geometry, so like these regions, in such a way that we actually fix the lattice property. Okay. And if you're interested, this is on my website, and you can see this for like other Coxeter groups also. Perfect. Okay, so what are these objects we're going to add? Okay, we've talked about separable sets, but actually, what we're going to want is something a little different, or at least seemingly a little different. So the sets that we'll care about are called biclosed sets. So here's the definition. So again, we're given a set of positive roots, and we want to check whether it's one of these biclosed sets. How do we do that? What we need to check is that for every triple of positive roots, alpha, beta, gamma, such that gamma is a positive combination of alpha and beta. So there's some way of writing it in terms of alpha and beta with positive coefficients. Then I want to check these two properties for every such triple. So one of them is the closed property, which says that if alpha is in my set and beta is in my set, then gamma is also in my set. And the other is the co-closed property, which says that if alpha is not in my set and beta is not in my set, then gamma is not in my set. Okay, this is sort of a mysterious condition. So let's just see what these look like for S3. So starting with my 3 positive roots, I could just take the set of all 3 positive roots, and that will always be biclosed. Okay, here's an example which isn't biclosed. I could just try deleting the middle root here. This is not closed because the middle root is a positive combination of the 2 outer roots, so I must be forced to put it in there. Okay, I could also try taking just the middle root, but now it's still a positive combination of alpha and beta, but alpha and beta are not in there, so I'm forced to not have alpha plus beta. Okay, every other subset is biclosed. So again, here are our 6 biclosed sets, and you'll say these look pretty familiar, and that is because they have appeared on like 15 of the slides so far. So these are, of course, the separable sets again. So let's see if we can figure out what's going on. So actually in dimension 2, the biclosed sets always coincide with the separable sets. And we can sort of take this as a definition of biclosed. So biclosed sets are the ones that you get by asking that for every intersection of your set with a 2-dimensional subspace, then you get a separable set. So it's like being locally separable. So we just want to ask that whenever I take a 2-dimensional slice of my root system, then the elements of my biclosed set actually form a separable set inside that slice.
Isn't this equivalent to being the inversion set? I mean, I know it is in the finite case.
Yes, in the finite case, this is still just the inversion sets. Yeah, that's it.
But not in the infinite.
But not in the infinite case. Yeah, in fact, all 3 of the types of things I've defined are different in the infinite case.
For like infinite dihedral.
Infinite dihedral, these are not the same thing as inversion sets, but inversion sets and separable sets and biclosed sets are the same. So they're not all 3 different for all infinite Coxeter groups, but in general.
So in general, separable implies biclosed.
Correct. Yeah, any other questions? Okay. All right, so what is extended weak order? It is just containment order on these biclosed sets. So my claim was that this is somehow adding elements to weak order. So let's see if we can figure out why that would be the case. So if I have, okay, so just, yeah, say this one more time. So the extended weak order of a Coxeter group is given by taking a root system for that thing and looking at the biclosed sets of positive roots. And the containment order on those is the extended weak order. So it is not an ordering of the elements of the group. I get that question. Okay, so here's just a extended weak order for finite 2 examples of finite Coxeter groups. You can see it's the same as the weak order. Here's what it looks like for that infinite dihedral group. Okay, so why exactly do these biclosed sets extend the weak order? Well, if you have a root system, then these inversion sets we were talking about before, the way of turning an element of the group into a set of roots, those are exactly the finite biclosed sets. So that answers your question from before. So sitting inside this poset of biclosed sets, at the bottom is the finite biclosed sets. And the finite biclosed sets are in bijection with the elements of the group, and their containment order is just the weak ordering on the group when we transfer it. So the extended weak order really does extend the weak order. And these finite biclosed sets, the ones that are associated to elements of the group, they also correspond to regions of the Coxeter arrangement. They're separable, but not every region, just the regions that are in what's called the Tietz cone. So here in shaded in blue, the same area that we were looking at before that corresponded to elements of the group, this is the Tietz cone for this affine S2. So extended weak order is kind of about understanding things that are happening outside the Tietz cone. Okay. So this is just restating what I said. So the collection of finite biclosed sets is isomorphic to the weak. Okay, so let's talk about some history. So finite separable sets, aka inversion sets, they're in bijection with the elements of the group, and so arguably they've been studied for a very long time. So there's various ways you can use them. Whenever you're thinking about elements of the group, you might be able to think about it as a set of roots, and sometimes that's natural. So those have been very well studied. These infinite separable sets have also been studied somewhat. So there's ways to write down like generalized Borel subalgebras of Cas-Moody algebras, or stability conditions for quiver representations coming from these things. Biclosed sets are more recent. So biclosed sets were introduced by Matthew Dyer, who was here, and Tom Edgar, who was a student here. Their original usage was for understanding things called reflection orders and twisted causal-linguistic polynomials. So they sort of have origins in causal-linguistic theory, but now they seem to have applications in a lot of different areas. So I'll talk about a few of those at the end. Okay, so Dyer, in studying this poset, had made some conjectures. He has made a lot of conjectures actually, but these are two, I would say, his two main ones. So he's called these conjecture A and conjecture B before. So what do they say? Well, if I have a Coxeter group, then conjecture A says that if I take a cover relation and extend a weak order, that would be a biclosed set containing another one with no other biclosed sets in between, then it's just given by adding a single root. So the only way I can step up and extend a weak order is by adding a single root. And then conjecture B says that this extended weak order is actually a complete lattice. So by adding all of the biclosed sets, we've sort of fixed the lattice property. We've recovered all of the missing things that we were looking for before. Okay, so those are conjectures. They're both still open in full generality. Yeah.
Sorry, I have a question about the definition of biclosed set. So in type 8.2 tilde, you only added one element, right? But shouldn't like the complement of a biclosed set also be a biclosed set?
Sorry, you said we only add one element to A2 tilde?
Or how many elements did you add to A2 tilde?
If you're thinking about the picture which looked like this,
Yeah.
then I added infinitely many.
Oh, okay.
Yeah. So it was like I had a U shape.
Yeah.
And then there's another upside down U shape on top of it.
Those upside down.
So it's not just adding a single element. That would be a way to fix the lattice property, is to just add a single element on the top, but that's not a very geometric thing to do. Yeah.
Related to what you just said, is there some sort of poset theoretic lattice completion that gives the extended weak order?
Not a poset theoretic lattice completion for anything that I know. Yeah, I mean it's the lattice completion of extended weak order if extended weak order is the lattice, but yeah, there's no natural thing you can do with weak order that's simpler than defining the biclosed sets for which extended weak order is the lattice completion. So it's not the lattice completion of the separable sets, for instance, or the original elements of the group. Yeah, other questions? Okay, so one point that might come up that you might ask is why not use the separable sets, these things that correspond to regions of the Coxeter arrangement? So I mentioned that we're going to be adding all these regions at the back of the Coxeter arrangement. Why not just add those and not whatever other biclosed sets exist? So here's one reason why you might want to do this. Dyer's conjecture A is fairly easy to prove for the separable set. So if I have a cover relation, an extended weak order, and both of these two biclosed sets are actually separable, then this cover relation is given by adding a single root. Okay, so why do we actually want to use biclosed sets? Well, in affine Coxeter groups, at least with rank at least 4, the separable sets actually don't form a lattice. So it's possible to find elements that don't have a join in separable sets. And so yeah, again, we still interpret this as saying that we have not found all the elements yet. But biclosed sets fix this. Okay, so progress on these two conjectures. So conjecture A, about the cover relations. So this is known for affine Coxeter groups. So Dyer has proven this. It's a paper that hasn't come out. And then with David's Dyer, we proved this a different way. And then recently, with Colin Defon, Trisha Hirsch, John McCammon, Thomas McConville, and David Dyer, we proved for rank 3 Coxeter groups that this, all rank 3 Coxeter groups that this cover relation fact holds. So this is actually 2 papers. The first one we just did it for the universal rank 3 Coxeter group. This is the free product of 3 copies of CMod 2. And then in a paper that we are writing right now, we extend this to all rank 3 Coxeter groups. Okay, so that's the cover relation conjecture. There's also the lattice property conjecture. So first of all, Bjorner proved that if you just take the finite biclosed sets and you just care about meets, not joins, so greatest lower bounds, not least separate bounds, then those form a meet semi-lattice. So if you just start taking meets, you can just use the elements of the Coxeter group and you already get a meet lattice semi-lattice. In 2018, Wei Zhao Wang, who I think was also a student here, proved that Dyer's conjecture B is true for the rank 3 affine Coxeter groups. So rank 3 and affine Coxeter groups, affine A2, affine C2, and affine G2. There's just a list of three of them, 3 irreducible ones anyway. Okay, and then with David, we showed that this conjecture B, the lattice property, is true for all affine Coxeter groups, so all ranks. And then again, with this large group, we showed that this is true for all rank 3 Coxeter groups. And then again, this is 2 papers, one where we did it for the universal Coxeter group, and one where we did it in general, in full general, which is still being written. Okay, so interestingly, this result is the intersection of these 2. So how did we do this? So in this, in both of the papers that I was involved with on the previous slide, we approached this in the same way. So the way we used it, or the way that we proved this, was using something called clean arrangements, clean hyperplane arrangements. So if I have a hyperplane arrangement and some set of normal vectors to the hyperplanes, so I could take my Coxeter arrangement and the positive roots, then I say that the arrangement is a clean arrangement if every biclosed set in that set of normal vectors is a separable set. So clean means that every biclosed set is separable. It's always true that every separable set is biclosed. So this is just saying that those 2 sets are actually equal. And then what we showed in the affine type paper was that if you take in what we call an ideal sub, or what is called an ideal subarrangement of a finite or rank 3 affine Coxeter arrangement, then you always get a clean arrangement. And this is the fundamental lemma in the paper. It's that if you take these ideal subarrangements, then every biclosed set is already separable. Interestingly, recently, Yoshinaga has proven that every finite k-pi1 arrangement is a clean arrangement. So this is the property that if I take my hyperplane arrangement, complexify it, delete all the hyperplanes, then the resulting thing is an island-Röggen plane space. Its only non-vanishing homotopy group is pi1. This is a property that. Oh,
So sorry.
Yeah.
What's an ideal subarrangement? Can you say again?
Yeah. So there's a
Every ideal subarrangement.
Yeah. So yeah, this is in quotation marks. That just means there's a poset on the roots called the root poset, and it's an order ideal.
Ah,
in
okay.
that poset.
Yep.
Yeah.
Okay. Thank you. What is k-pi?
That means that every homotopy group except pi1 vanishes. Yeah. So another way of saying that is that the universal cover is contractible. Other questions? Okay, and so I mentioned the fundamental lemma from the paper about affine type was proving that these ideal subarrangements are clean arrangements. Well, the fundamental lemma, or theorem really, from this paper, excuse me, with the many authors, is that every rank 3 Coxeter arrangement is already a clean arrangement. And the way that we prove this is we use snakes on the hyperbolic plane. So we need to show that every biclosed set is separable. And so what we end up doing is kind of encoding the biclosed set with the two colors red and blue here, and writing down a little snake that separates the red from the blue. And by looking at the two endpoints of the snake, we're actually able to explicitly construct a hyperplane that separates that biclosed set. So it's a pretty neat graphical argument. And we have a generalization of this argument for every rank 3 Coxeter arrangement. So this is for the universal Coxeter group. Okay. And I want to point out that rank 4 affine Coxeter arrangements are not clean. So there exist biclosed sets that are not separable. This follows from what I said earlier about the lattice property not being true for the separable sets, but it being true for the biclosed sets. So there must be biclosed sets that aren't separable. That's not how we prove it. You can just write down explicit examples. These things are very combinatorial, so you can just list them out, at least in that method. Okay. So speaking of them being very combinatorial, the next part I'm just going to tell you about the combinatorics. So there were other questions about the geometry and the conjectures. Yeah.
Just make sure I put these things together. So in rank 3, biclosed if and only if separable.
Correct. Yeah, so in fact, in rank 3, all we're doing is adding in the regions. But in higher rank, we actually need to add some mysterious other things. Other questions? Yeah.
Does the existence of these rank 4 examples cause you to doubt conjecture A, or is it just that the
No, we can also prove conjecture A when those examples exist. Yeah. It's just harder to prove. Yeah. Yeah, in fact, David Spire and I have a method for sort of proving conjectures A and B that depends on the cleanliness property only in rank 3, but for these ideal subarrangements. And we just don't know that for all Coxeter groups. Okay, any other questions? Okay, so now we can basically start from scratch because I'm just going to tell you how you can use combinatorics to list the biclosed sets in these two types. So this is S infinity, like the symmetric group that's bijections of the integers with itself, and this is the affine symmetric group. Okay, so let S infinity be the bijections of C with itself that fixes all but finally many integers. This is a Coxeter group. If you're thinking about Coxeter diagrams, it's the one that's bi infinite, so the one that goes off to infinity in both directions. What does extended weak order look like for this group? Well, to kind of motivate the answer, let's look at an example. So here's a sequence of permutations of the integers that's in this Coxeter group. So what I can do is I can take 0 and move it farther and farther to the left. So this gives me a sequence of permutations. One is the identity, then here I've swapped 0 and -1, and then here I'm just like moving 0 farther and farther left, right? Okay, this is an increasing chain in weak order. So in the extended weak order, it should have a join, so it should basically have a limit. We want a limit of this sequence. Okay, whatever this limit is, it should have 0 to the left of every integer. Okay, so it looks something like this. This is not a permutation. This is not a bijection from Z to itself. But it is a way of ordering the integers. So it turns out, and this will be the answer, it turns out that the orderings of the integers are the biclosed sets for the S infinity. So how does this work? Well, if I have a total order of the integers, I'll call it like triangle Sn, then I can talk about an inversion of that total ordering. That'll just be a pair I comma j, such that I is less than j in the usual ordering of the integers, but I is greater than j in my particular total order. Okay, and so if I associate it to a permutation of the integers to this particular total ordering, the one-line notation, basically, then this is the same thing as the inversions for that permutation. Okay, so if I write tot of z for the set of all total orders of the integers, I can talk about an inversion set. And then I define the weak order on total orderings of the integers to be containment of inversion sets. And then the theorem is that this is actually a complete lattice. And also that this complete lattice is the extended weak order for S infinity. So what is like the bijection between our total orders and our biclosed sets? Well, we just send our inversion set to a set of roots in sort of the canonical way. We turn the pair ij, which was inverted, into ei minus ej. Okay, so we got questions about S infinity?
Are like people in other areas interested in these total orders?
Yeah, I think they have something to do with Frazee limits and something. I've got an email from somebody about this before, but I don't know too much about it. Some area of set theory. Okay, any other questions? Sorry. Well, I mean, it's hard to actually write down what an element of this is. There are certain elements that you can definitely write down, but like there's uncountably many total orders of integers. So the question is, in what way are you presented the total order? But usually, I mean, I would say yes, if allowing for certain ways of handing you a total order. Yeah. Like I can tell you whether any particular inversion is in there if you tell me in enough detail which inversions were in the original set of things. Okay. All right, so now for the affine symmetric group. It'll turn out that the story is pretty similar. So the affine symmetric group, it's the group associated to this affine type A root system. But there's also a combinatorial way of describing it. It's the group of bijections from the integers to themselves, such that if I add in to the input, then it's the same thing as adding in to the output. Okay, there's also a normalization condition which says that if I sum the first in outputs, then it's the same as summing the first in inputs. Okay, so this is a Coxeter group, the affine type A Coxeter group. Okay, and there's the root system again. So one way of building this root system would be to just tack on deltas to the type A root system. Another way is to say that we could say that the roots are given by like alpha I comma j with a tilde over it for just like pairs of integers I and j. So there's a way of like making a vector space in which these vectors live, such that this is actually the root system. So the way you do it is by modding out by the relations that alpha sub I comma j is the same thing as alpha sub I plus n comma j plus n. And also when I add two vectors that have the same endpoint, they sort of merge. Okay, and so what is the root system of the affine symmetric group using this labeling? It's going to be the set of all alpha ij where I and j are not congruent mod in. So why did we drop the ones that are where it's congruent mod in? They aren't in the root system as I've defined it. The thing you get by doing alpha I comma I plus n is the imaginary root. And so this whole story about biclosed sets is just focusing on those real roots. Okay, so how do we describe the extended weak order? Well, if I'm given a total order, then I can just take its inversion set and forget all of the pairs which are not congruent, or which are congruent mod n, leaving only the pairs which are not congruent mod n. And this will basically be the operation which will give us some like sets of positive roots for affine type A. And we don't want to apply this to just any total order though. What we'll do is we'll say that an order is translation invariant if for all I and j, we have that I is less than j in our order if and only if I plus n is less than j plus n in the order. So translation invariant by n. Okay, and now what are our biclosed sets for affine type A? They are just basically the same thing as the translation invariant total orders, but we do this forgetful operation, which forgets some of the inversions. Okay, and then there's a very explicit way of parameterizing these things using window notation. So these translation invariant total orders. I mentioned earlier that all total orders on the integers there's uncountably many. They're very hard. They're not very well behaved. It's hard to even like specify one. But these translation invariant total orders are completely combinatorial. You can specify one with a finite amount of data, and you can list out all of them you can list out all of them in a computable way. So there's countably many in particular. Okay, so there's a nice combinatorial parameterization using, and the one way to do this is using window notation. So I'm not going to talk about that, but if somebody has questions about it after, I can tell you that. Okay, so the the last thing I want to talk about is applications of biclosed sets. But are there any questions about the combinatorics first? All right, so I'm gonna give 4 applications. They're gonna be in like different areas of math. So if you're not familiar with the area of math, feel free to just ignore the current application. All right, so application 1 is to Coxeter matroid polytopes. So if I have a Coxeter group and its root system, then I can define the notion of a Coxeter matroid. So what I'm going to do is I'm going to take some vector rho, which is not fixed by reflection over any root, and then I say that a finite subset of my Coxeter group is a Coxeter matroid. If I take the polytope, which is so I have a subset X, and I'm just going to take every element of X and hit my starting vector with that element. And so that's going to give me a list of points in space, and I take the convex whole of those. And my original set is a Coxeter matroid if every edge of that polytope is parallel to some root. Okay. So now what I'm going to do, now that I have a Coxeter matroid polytope, is I'm going to take the one skeleton of that polytope. So just look at the edges. I'll turn it into a directed graph. And I'll just point the edges in the negative root direction, just because that's slightly nicer for some reason. Okay, so that's G sub X. Okay, and so here's a conjecture. So if I have one of these Coxeter matroids, and I have a biclosed set, then what I can do is I can reverse all the edges of that graph, which are parallel to roots in the biclosed set. So remember, edges here are edges of this polytope, and I need that the edges of the polytope are parallel to roots. So there's some way to line up roots with edges. All right, and I'm going to reverse the edges which are parallel to roots that are in my biclosed set. So the biclosed set is telling me which edges to reverse. The conjecture says that the resulting graph is acyclic and has a unique source and sink. Yeah.
So is the Coxeter group finite in this case?
No, infinite Coxeter. It's this is a theorem for finite Coxeter groups.
Polytope in the infinite.
The subset is finite. Finite subset.
Okay. So by passing to a finite subset, you can't pass to a finite root system that contains. Okay.
Yeah, so you can have like a even a rank 2 root system, which is infinite. Yeah, and you still need so it's true that like no matter how many roots you take, there's not if you take more than 2 roots, then there's not like another smaller subsystem containing it. Yeah, other questions? Okay, so I'm going to give you an application of this conjecture, which will be application 2. Okay, so this is for Bruhat decompositions.
Sorry, I had a question about application 1.
Yeah.
You said it's a theorem for finite Coxeter groups?
Yep.
Is it some property of Coxeter matroids that I would
Yes,
know?
this is the fundamental theorem of Coxeter matroids.
That there's a unique thing in, like, it's like the.
Yeah, so this is the W-twisted Bruhat order.
Okay, great.
Yeah, exactly. Yeah, they're defining like W-twisted Bruhat order for where W is a biclosed set instead of an element of the group. Right. Yeah.
In like type A, is this like the greedy algorithm on basis of matroids is like well defined or something?
Oh, I think that's a little bit stronger, but I'm not sure. Okay. Oh, I see what you're saying. Yeah, because of the unique source and sync. Yeah, that probably is what it. Yeah, that's probably what. But it'd be on flag matroids here. Yeah.
Oh.
Of course, you could do a parabolic version of that. I'm not sure what the correct statement would be. Yeah, other questions? Okay. So an application of that, so this is just that same conjecture right here about the Coxeter matroids. A corollary of that conjecture is that if I have a Kac-Moody group, G, so this is like the Lie groups associated to infinite Coxeter groups. And I have a Borel subgroup B, and I have a biclosed set of roots, then there should be some twisted Bruhat decomposition, some way of writing the group as a disjoint union over the elements of the vowel group of some subgroups times W times B. Or actually, I'm not even going to ask that the use of W's are subgroups, they're just going to be products of roots and groups. So there should be some way of decomposing the group according to what the biclosed set tells you. And this way should be different for each biclosed set. So we we actually get new decompositions from the new biclosed sets. Okay, this is a little bit of a weird way of saying that. If you've ever seen the usual Bruhat decomposition, you're used to there being a B right there. Okay, so that conjecture number 2 here will be about fixing that. So this is sort of a Lie theoretic analog of the Coxeter matrix conjecture. Okay, so this conjecture says that if I have a Kac-Moody algebra G and the root system is phi, and a biclosed set of positive real roots, these are still the real roots, then there's a subalgebra such that the real root space is in the subalgebra if and only if the root is in the biclosed set. Okay, so what am I saying? I'm saying basically that if I take the subalgebra generated by the real root spaces for the alpha in my biclosed set, and the, I didn't say this part, sorry, and the negative real root subspaces for the alphas not in my set, then I want that subalgebra to not change. When I start like taking Lie brackets, I want there to not be any new real root spaces. So some sort of algebraic version of the biclosed set condition would be what this would entail. Okay, so this would mean that the biclosed sets are exactly the positive roots that appear in some sort of like generalized Borel subalgebra. These subalgebras here, you think of them as some sort of generalized Borel subalgebra. And if this conjecture is true, then this twisted Bruhat decomposition from the previous slide is actually a decomposition into orbits of some generalized Borel subgroup. So we would basically take the subgroup of G corresponding to the subalgebra, and then this would be the orbit decomposition for that subgroup. So this conjecture is saying that biclosed sets are really telling us about these generalized Borel subgroups. Okay, so questions about the application 2? Yeah.
Nice.
There are some that come up in affine type that are actually fairly well studied. So these conjectures, both of the ones so far, are theorems for separable sets. And so in affine type, there's some particularly nice separable sets that give you decompositions of Lie theoretic significance. The conjecture is saying that we should get different decompositions also for these biclosed sets that aren't separable. Any other questions? And I think I can prove this one for affine type, but I haven't written it down, so I'm not sure. Okay. All right, so application 3 is to cluster algebras. Nathan's smiling. Okay, so associated to each loopless 2A cyclic quiver is a cluster algebra. So quiver is just a directed graph. Okay, so I'll just write A sub Q for the cluster algebra associated to the quiver Q. And the way that this works, obviously I'm not going to define it, but is that we'll have a variable associated to each node in the quiver. And then there's a notion of clusters in the cluster algebra. Those are just sets of Laurent polynomials in the variables. The way you build them is by starting with the set of starting variables and then doing mutations on it. And that gives you new sets of variables, and those are the clusters. And then you can write down a graph called the exchange graph. The vertices are just the clusters, and the edges are the mutation relation. So I would go from this set to this set by mutating at x1. And so we get a graph. If you do it for this quiver right here, it looks like a pentagon. Okay, and so here is another example. If I do it for the affine type A1 quiver, which looks like this, then I get this sort of picture. This half might look familiar from earlier. Okay, so here's the observation. This is a picture of the extended weak order for affine type A1. Same picture from before, but I just turned the roots into dots because it was messy. How do I go from this picture to this picture? Well, I basically just squish everything on the brain. Okay, so the first of all, there's a theorem which says that if I have an orientation of an affine Deakin diagram with an affine Coxeter group, W, then there's a quotient of the extended weak order of W, which realizes the ordered exchange graph of the cluster algebra. So these are called affine Cambrian quotients. The reason being that this theorem are also known due to Nathan Reading for finite type quivers, finite type Coxeter groups, and there it's called Cambrian quotients. So one could conjecture that if I have any acyclic quiver and I interpret it as a Coxeter diagram for some Coxeter group, then there should be a quotient of the extended weak order, which realizes the ordered exchange graph for the cluster algebra. So there should be some way of turning the Hasse diagram of extended weak order into a exchange graph for a cluster algebra. And the process should look something like what we did here. It should look like squishing stuff. So more precisely, there should be a lattice quotient of extended weak order. That's the conjecture. So questions about this conjecture? Yeah.
You have the graph, like you have those limit points. How do that?
Which
So on the left, you have
Yep.
a freehold graph. How does the free graph has a limit point?
the quiver graph doesn't have a limit point, just because there's not a notion of a limit of a sequence of mutations. Or I would bet there probably is a notion of that, but I am not familiar with this notion. Yeah, so there's not actually a point there in the mutation exchange graph. What's going on is that we do this quotient operation, and then we take the connected component of the bottom element, and that's the thing that should be the exchange graph. Yeah. Other questions? So one more application. This is probably the least familiar people in the audience. So this is an application to representation theory of algebras. So what we can do if we're given an algebra, usually a finite dimensional algebra, but actually not in this case, then we can define something called a torsion class. So this is just going to be a collection of finite dimensional modules, which is closed under quotients, taking quotients of a module and taking extensions. If I look at these torsion classes, they're sets of modules. I can think about containment order on these sets, sort of like extended weak order is containment order on the biclosed sets. And it's known that the torsion classes form a lattice under containment.
Algebra associative, commutative?
Associative, not commutative. Yeah. Yeah, so this is representation theory of associative algebras. Yeah. Okay, but turns out that if you have an affine Coxeter group and you look at its extended weak order, there's actually another way of making the same poset. So what you do is you take something called a pre-projective algebra, some algebra you can define, and you look at the torsion classes. That forms a poset under containment. It's a lattice. And there's a certain quotient you can do to it, which actually just gives you the extended weak order. So this poset of biclosed sets has a realization coming from algebra. Okay, so one might conjecture that this is true for all extended weak orders, or at least where you can make sense of the pre-projective algebra. So if I have a crystallographic Coxeter group, those are the ones for which you can make sense of the pre-projective algebra. Then we could conjecture that the extended weak order of W is actually a quotient of the lattice of torsion classes of the pre-projective algebra. So there should be some algebraic incarnation of extended weak order. And I think that's all I have to say. So thank you. Questions for Grant?
So if I got the directions straight, you're saying that in general you expect extended weak order is a quotient of this lattice of torsion classes, and the exchange graph is a further quotient.
Yes.
Taking weak order out of the middle, is there any known connection?
Yes, it is known that the exchange graph for the cluster algebras can be made by starting with the pre-projective algebra torsion classes and doing a quotient.
If there are no more questions, let's find Grant again.